There are still
It's early morning.
there are so many students in this travel office.
You come from the US, right?
No, I was
Oh, no, I didn't want to. It's all right. We can chat later.
well, let me.
Last lecture. Okay, good morning. Let's begin our second day with the last lecture on amplitudes.
Okay, thank you. So today is the last lecture. So let me first a little bit more extensively review the first two lectures and where we are going in the end. Okay. So the question I posed in the beginning is, from the theoretical point of view, what is the content of the scattering process? Or in other words, if I have some initial and final states, what is really sitting in this blob? Yeah, how can we theoretically describe the interaction? And the standard picture tells us that it's a sum of Feynman diagrams, or all possible exchanges of particles that can happen, the virtual particles that can happen, and the perturbation theory gives us the systematic picture how to calculate it, when the simpler diagrams should dominate at weak coupling, and then we are going to higher and higher orders, and we have to draw more and more complicated diagrams. And the rule is that we have to draw all of them at a given order to get the full result. Now, the standard way how to do it is to start with Lagrangian. Like this is a Lagrangian for the Yang-Mills theory, or gluodynamics. We have some kinetic term, we have some interaction terms, like here 3-point interaction, 4-point interaction, and we just draw all Feynman diagrams. This is at 3 level for a certain number of external gluons, and we have to sum everything. We have to draw it, evaluate it using Feynman rules, sum everything, and that's the result for the amplitude of that process. Now, I showed that what we started with as a motivation was the calculation from 1985, which was exactly that process, 2 gluons in the initial states and 4 gluons in the final states for particular helicity configuration, and that was 220 Feynman diagrams, and this was the result in the paper. And but the final result for the amplitude was as simple like that. Yeah. And I already introduced these spinor helicity variables. This result was not originally written in terms of spinor helicity variables. It was rewritten like that a few years after that. Now, this kind of poses a question why the final result is so simple and Feynman diagrams don't make that simplicity manifest. And the point of view that people got after that was kind of a revival of the analytic S-matrix program from 60s, when also people tried to think about the amplitudes in a very different way, not as a sum of Feynman diagrams. Well, there were no Feynman diagrams at that point, or there were Feynman diagrams at that point, but for example, for QCD, the theory wasn't known, so there wasn't a way how to use that, how to use this machinery to actually give the predictions, for example, for these gluon amplitudes. But the approach there was that the amplitude is some unique object which is fixed by some physical properties, like the factorization. Unfortunately, this wasn't successful back in the 60s for many reasons, especially because they didn't do it in the perturbation theory. They wanted to fix the amplitude as one object to all orders, complete non-perturbative. And they were also not considering massless particles, but massive, and there are more abstractions. So that was one point of view back in time. The other point of view is the standard approach using Feynman diagrams. And the modern methods actually use both of them. Use perturbation theory on one side, but try to calculate amplitude at a given order in perturbation theory directly, not using Feynman diagrams, but trying to fix it completely using certain properties, using constraints. And the two constraints I mentioned was the locality constraint, the fact that the particles interact point-like in the space-time, which translates in the momentum space to the presence of 1 over p square poles coming from Feynman propagators, where p is the sum of external momenta. So the only poles of tree-level amplitudes look like that. And the unitarity at tree level is the statement that the amplitude on such a pole factorizes into two pieces, where p is now the sum of the external momenta on left or right. Using momentum conservation, it's the same. So the factorization property is the statement about perturbative unitarity at tree level. Now, the loop level unitarity is an analog from tree level, but the statement is that if we now sit at two different poles, now this thing is a loop amplitude. Now we don't want to, normally what we would do is to write Feynman diagrams. Each of them has some loop momentum dependence. We would have to integrate over that and then sum the results. But the statement about the loop level unitarity is before you integrate. So you don't integrate, you just leave the integral, the integration untouched, and you just look at the integrand before you integrate. Then if you combine everything, and you set two of the propagators to 0, the one loop amplitude factorizes into products of trees. So the loop is kind of hiding here, and then you have two tree-level amplitudes, and then you have these two poles that on which you are sitting. These two propagators you set to 0. And this generalizes to high loop order, so it can be L loop amplitude, and then it factorizes to two lower loop amplitudes where the sum of the loop degrees is L minus 1. You're always losing one loop degree here inside. So that's also the statement about unitarity now at one loop and higher loops. And actually, this is the fact setting the propagator to 0. We normally call it cut, because we kind of like cut the propagator. It's on shell now. And this is the statement of unitarity cut. But there is an iterative procedure how to continue and obtain higher cuts. Now, the viewpoint, or the new viewpoint here is that the final answer is completely rigid, it's fixed, after we provide some input. So that was already, this is kind of already underlying Feynman diagrams and that approach, where the input is Lagrangian. We give Lagrangian, then there is a machinery of Feynman vertices, drawing Feynman diagrams, evaluating them, summing them. So the Lagrangian is an input. Now, in these new methods, it's not a Lagrangian which is input, but it's the physical properties of the amplitude which is input, which is the gauge invariance, the fact that the amplitude are gauge invariant, as we discussed before. And also this locality and unitarity property. So the fact that the only poles are of the form 1 over p square, or that loop level 1 over L square, which also involves the loop momenta, and the fact that the amplitude must factorize properly on these poles. So this is this tree-level factorization and the loop factorization. So that's an input. for us. So here it was kind of an output. Of course, everything is the same quantum field theory, so it has all these properties, but it's a different starting point to the same thing. And then the statement is that the amplitude is a unigauge invariant object which factorizes properly on all channels. And that's true for a very large class of quantum field theories. For certain theories, we have to, we might provide some extra information, but this is the essential statement. And all theories, basically all theories we know do satisfy it. Now, how to use it to actually as a computational tool? So we mentioned these unitarity methods, which date back to early 90s, which from some point of view is a very smart reshuffling of the Feynman expansion. So I have a loop amplitude on one side, and instead of writing it as a sum of Feynman diagrams, I already choose the basis of all possible integrals that can appear in Feynman diagrams. And then I put some unknown coefficients there. Then I perform these cuts, which gives me linear system of equations for these coefficients. So on the right-hand side, I would have linear combinations of coefficients. If I impose the cut, it will just eat up the integral. It just gives, maybe in the end, it gives some function of external kinematics, but no loop momentum left. And on the left-hand side, I get a product of three-level amplitudes. So this is a system of equation I get. I know all three-level amplitudes using different methods, and I get linear system for these coefficients. I solve it, and from that, I get the loop amplitude. Now, practical problems or challenges is that first I have to find the basis of these integrals and calculate them once. It's only necessary to calculate them once, and then I can do it in any theory and for any process, but I have to find the basis and calculate them, and then I have to solve the system of equations, and for higher and higher loops, it might be huge systems, thousands, 100,000, millions, and so on. So that's the challenge I have to do. But of course, if you compare, it's very efficient and successful approach if you compare it to Feynman diagrams, because at the loop level, the combinatorics of Feynman diagrams explodes, and you, at even a not very high loop order, like 2-loop, 3-loop, we are already encountering like millions of Feynman diagrams, even for simple processes. So it's completely intractable to do it like that. So this is the approach which is basically used for many of the calculations today. And as I mentioned, the cuts, which will also play role later, is just the iterative use of this three-level cut and the loop cut, when I can, for example, start with this unitarity cut and further factorize the three-level amplitudes in the corners using that. So then in the end, I cut more and more propagators, but I always get a product of three-level amplitudes here. Cutting these 3 propagators, I get a product of 3 three-level amplitudes. Cutting 4 propagators, which is a maximum at 1 loop that I can possibly cut, I can get a product of 4 three-level amplitudes. And I can do it at higher loop order because these blobs can be also loop amplitudes that I can further cut by setting more propagators to 0. Like this, if this is 1 loop, I can further cut 2 propagators here and then more here using these relations. So this is the system of cuts, and that provides me these linear equations for coefficients. Then what came much later was actually the new method for calculating three-level amplitudes. So for loops, it was very important that these unitarity methods worked. For three-level amplitudes, there were some other reshuffling of Feynman diagrams using some off-shell recursion relations and so on. But there was a big discovery in 2005 when Brito, Cacciazo, Fenk, and Witten constructed completely on-shell recursion relations. So now we are not dealing with any reshuffling of Feynman diagrams, nothing like that. We want to deal only with on-shell gauge invariant objects, which are amplitudes. So, and that was the way how to calculate a higher point amplitude as a sum of products of lower point amplitudes. And as we discussed last time, you cannot do it directly. You cannot take directly the product. You have to do some momentum shift of two of the external particles, for example, 1 and 2, and then these lower point amplitudes on left and right are evaluated at certain point in the complex space of this shift parameter, right? Especially in particular this value. But this is a recursive procedure, so if I know 6-point amplitude, I write it as a product of 5-point and 3-point, or 4-point and 4-point, and I have to sum over all factorization channels which keep the shifted legs each on one side, because if they are on the same side, then effectively there is no shift on the intermediate leg. So I cannot approach that factorization channel by tuning this shift parameter z. So this is the way how to write a higher point amplitude as a product of lower point amplitudes. And it's recursive, of course. If I want to recurse all the way down, I land up on 3-point amplitudes. Now, so both of these methods are very efficient, and it's now a standard toolbox for calculating amplitudes. But it's, in a sense, it's based on very conservative ideas of applying general principles to uniquely fix the answers. It's not new principles. We already know all of them. Yeah, these are principles of quantum field theory that can be also seen in Feynman diagrams, but we revert the procedure and we use them as constraints. But the main goal for some of the people of looking at amplitudes is find some completely new picture for scattering amplitudes and presumably then also for quantum field theory. And of course, there is a complementary approach, which is finding the most effective computational way how to calculate amplitudes. And these methods I showed are the state of the art at the moment. But these two motivations kind of also come together. So let me proceed more on that in this talk and try to see if the amplitudes can be also obtained from a completely different point of view, when we don't kind of recycle the properties that we know, locality and unitarity, but we start with a different starting point. Yeah? Of course, we have to land on exactly the same result. We are calculating the same amplitudes. But we want to start from a completely different point of view, which actually doesn't use any of the words, doesn't use Lagrangian's Feynman diagrams, but doesn't even use locality and unitarity, and to see if something like that exists. There is no guarantee that something like that would exist. There is no reason why it should exist, but at least in a very special case, it does exist. So what is next? And I again go back and I start to talk about 3-point amplitudes again and on-shell diagrams, because this is our gate to this new world. And just to remind you, we discussed the 3-point kinematics, and using spinor helicity variables, we found that for complex momenta, there are two solutions how to solve the on-shell conditions and momentum conservation at 3-point. And it's that for the free momenta, either their lambda spinors are proportional or their lambda tilde spinors are proportional. That's just kinematics. And then from that, and using the Lorentz symmetry, we can completely fix the form of the 3-point amplitudes in any theory. It doesn't depend on theory, it just depends on the helicities of external particles. So the 3-point amplitude is completely fixed to all loop ordering perturbation theory. It's just kinematics. And there were two options. The first one corresponds to having all lambdas proportional, because all these angle brackets are 0. So the only thing that we can write are these square brackets. And if you just solve these relations, you find that you get these 3 remaining square brackets that are left with these powers of h's, where h is the helicity of these 3 particles. And this applies when the sum of helicities is bigger than 0. When it's smaller than 0, then we have the other option with the other solution to 3-point kinematics. Now, this is for particular helicities. So again, it's completely agnostic to the theory. It kind of defines the theory. The theory is already defined. The theory with 3-point interactions is already defined by the particle content, saying what are the elementary 3-point amplitudes here. Now, the supersymmetry, if we add supersymmetry, which we don't have to, but it's a very convenient tool because it allows us to talk about many different helicities at the same time. So all component amplitudes are included if there are superfields here instead of elementary, just the component fields with given helicity. We can also construct the 3-point amplitudes. And for example, if we had maximal supersymmetry, there are many nice things about it. Again, it's not necessary to do it, but for the purpose of the rest of the talk, I will just show it because this is what we will work with. This is the form of the 3-point amplitudes. Here you see that the same structure in the denominator of these angle brackets. There is a momentum conservation, and there is also something called supermomentum conservation, where the eta tildes are fermionic variables in the expansion of the superfield. I will show the slide with that a little bit later. But the important thing that these 3-point amplitudes are fully fixed in any quantum field theory. The supersymmetry gives us easy bookkeeping because now I don't have to specify what are the helicities of particles flowing in these lines before I had to here. So then if I glue them together, I have to specify what is the helicity coming in and out. They are conjugate, but because the n equals 4 supermultiplet is self-conjugate, I don't have to specify any helicities. Everything is flowing in these lines. But again, it's just for convenience, because then if I glue it together, I can get diagrams like that. So we call it on-shell diagrams because all the lines, both external and internal, are on shell. It's not a Feynman diagram. You can draw a Feynman diagram like that in any theory, phi cube or Young-Mills theory. But then that would be a one-loop diagram with these propagators being off-shell. But this is on-shell now, so it's very different. And these are not Feynman vertices by 3-point amplitudes. So in n equals 4 super Young-Mills, I don't have to give any information about the helicities on these internal lines. If I have in any other theory, I would have to say what is flowing on these lines. Now, because these are products of 3-point amplitudes, they are directly gauge-invariant functions, and therefore they are interesting to study. And they are well defined in any QFT. It's not obvious if they are useful for something in any QFT, but they are gauge-invariant functions which are well defined, and we can calculate them and study them. Yes?
If we don't have to worry about the helicities now, what do the white and purple dots represent?
Yeah, well, that's a very good question. So we don't have to worry about particular helicities, but there is kind of an overall counting. Yeah, so if, for example, indeed, there are all helicities here included, but still the two different vertices differ. So it contains a 3-point superamplitude. Then if you go only, some resonance here, to the gluonic sector, you would get minus minus plus or plus plus minus. Yeah, you get only one of these options for a given 3-point amplitudes. You also get amplitude with fermions and scalars, but there is something called R charge of the amplitude, which comes from the supersymmetry. So there is only a given value, amplitudes with a given value of this R charge. Yeah, you can think about it that if you just look at gluons, you forget all the rest. It would be the same as in Young-Mills. It would be minus minus plus for that one and plus plus minus for that one. Yeah? So it's not completely everything there. There are all the particles in the multiplet, but there is still some counting, which one can easily understand as counting of gluons, negative and positive helicity gluons. So there are still two different vertices, even in the supersymmetric theories. Okay, so now the natural question is, can we use these diagrams to build an amplitude from them? That would be the useful application. And as we showed, it's true, and in a very easy way is because these recursion relations we discussed, the BCFW recursion relations, have natural home in terms of these diagrams. So each term in this recursion can be represented as one of these on-shell diagrams. And there is actually a very nice diagrammatic way how to build these recursions. So if you have a left amplitude and right amplitude, suppose that I already calculated all of them and I store them. I just put left here, I connect with a line right here, And then there are these two legs I was shifting, the momenta of these two legs I was shifting, so I put such a bridge on top of that. Yeah, so here I am shifting 1 and n. And now I have to sum over all possible left and right amplitudes, which are consistent with the factorization of the amplitude I'm trying to calculate. So this is an example of 6-point amplitude, when I have 5-point amplitude on the left and 3-point on the right, or 2 4-points, or 3-point and 5-point. So I'm just drawing the diagrams which are non-zero. There are also many other diagrams which happen to be 0. For example, I can also put the black dot here, but there is some overall counting of helicity. So you have to say if you are interested. The 6-point amplitude still can have different helicities. It can have 2 minuses and 4 pluses, 3 minuses and 3 pluses, or 2 pluses and 4 minuses. So that gives me the counting of these black and white or blue and white dots that I can possibly use in the diagram. Again, if this is in terms of gluonic amplitudes, if we boost it to the 4 superfields, it's some counting of the R charge. So this is an implementation of the known method in this language. So this language of these on-shell diagrams, because now I don't think about this diagram as a 5-point amplitude and 3-point amplitude with momentum shift. Of course, this is correct, but this is not the way how I think about it. I think about it as this on-shell diagram, which means a product of 3-point amplitudes in these corners. This is the way I think about it. It's the same answer, but the on-shell diagram is defined like that. Now, again, the on-shell diagrams are natural gauge invariant objects, and they are, again, because the 3-point amplitudes are completely fixed, they are also completely fixed, yeah, because they are just products of 3-point amplitudes. Now, the recursion relations in this language work. We know how to implement these VCFW recursion relations. For constructing all amplitudes in renormalizable theories, including standard model, we need more general recursion relations, not just these ones. The question is how to implement them in these on-shell diagrams. We don't know it yet in full generality. And especially at loops, we know almost nothing about how to calculate loop-level amplitudes using these diagrams. We don't have working recursion relations at loops at the moment, except a very specific case of actually this n equals 4 super-Yang theory, when we know much more. But in general, we don't know. So these are all future challenges how to do it. But these diagrams exist in any theory, so they are natural building blocks for this potential line of research. Okay, so now the input are 3-point amplitudes, as I mentioned many times. This is fixed by Lorentz symmetry and the helicities. Kind of, there is still the same physical origin as in Feynman diagrams, because we are doing it in a different way. We are talking about 3-point amplitudes, not Feynman vertices. We are not talking about off-shell, but on-shell things. But there is still physics in the beginning. There is a Lorentz symmetry. There are the helicities of particles. So it's based on the idea that this fixes everything, but there is still this physics origin. However, very surprisingly, talking about these on-shell diagrams, there is a very different starting point to these objects. There is a very different interpretation of the same diagrams in mathematics, and there will be a very surprising connection to physics in the end. So this is exactly, so therefore I'm saying that the on-shell diagrams is a good gateway to trying to get the amplitudes from a complete different starting point, because the on-shell diagrams themselves already also have a very different interpretation. So let's see where this goes and how this is related. But before that, I have to restrict myself. I cannot do it in full generality. As I said, these on-shell diagrams exist. I will be able to say also a little bit more general, in more general field theories later. But for most of the rest of the talk, I have to concentrate on one particular case. Yeah, I cannot make progress on all questions at once. And I have to pick one special theory. And again, it will be this theory with maximal supersymmetry. But there is a very good motivation how to pick this particular theory and try to study it in more details. And that goes to, it has actually a very long history. And the motivation is that we always, if we want to make a progress on some very difficult question, we have to pick some model, or toy model, and that's a time-proven method how to make progress in general. And there is a very long history of certain type of models called integrable models, which are exactly solvable. And it started 400 years ago with Kepler problem. As you know, we can study the orbits just in classical mechanics in the potential with arbitrary power here, 1 over r to the arbitrary power. But something very nice happens if there is a first power. And the orbits, in that case, don't precess. But the reason for that is that there is a hidden symmetry. And it's the conservation of Runge length vector. And that allows us to solve that problem completely. And there is a special solution for that. This actually continues from classical to quantum mechanics. And in quantum mechanics, the same situation happens with hydrogen atom. So if we consider hydrogen atom with, again, the same potential, there is a hidden symmetry in that problem, which is not there for arbitrary spherical potential. And that's, again, a conservation of a special vector, now called Runge length Pauli vector. So there is, again, a hidden symmetry in the hydrogen atom that allows us very easily find the spectrum of hydrogen atom. And exactly the same thing happens for quantum field theory. And the special theory, which has a hidden symmetry, which is not there for any other quantum field theories, is maximally supersymmetric extension of the Yang-Mills theory and farther in the planar limit. Now, I will discuss what the planar limit means, but there is some SU and gauge symmetry in this theory, like in the usual Yang-Mills theory. And if we set n, the number of colors, to infinity, the only diagrams which contribute for calculating amplitudes are planar diagrams. Therefore, we call it planar. But otherwise, it's SUN gauge theory with n goes to infinity. Now, what is special about this theory? Well, it's still a theory of quarks and gluons. So the supersymmetric extension of the Yang-Mills theory has only gluons in it. But of course, the super Yang-Mills theory has all kinds of particles. It has scalars and also fermions. So, well, we can call them quarks, despite they are in a different representation. They are in adjoint representation, unlike quarks in QCD. Now, the theory behaves very similarly like QCD in many respects, but also it's very different. For example, there is no confinement. So it's a conformal field theory, so the coupling constant doesn't run, so it's valid to all energies. The spectrum is the same to all energies. The amplitudes are valid to all energies. The coupling constant is just a number in that case, so there is no confinement. However, from the practical point of view, if we, for example, concentrate only at 3-level amplitudes, the 3-level amplitudes in this theory are the same as the 3-level amplitudes in QCD for gluons. Yeah, of course, there are other particles here. There is even a way how to get the amplitudes of quarks from QCD from this theory, despite the quarks are in different representation, but there are some tricks how to do it. So from the 3-level point of view, it's actually extremely good bookkeeping of things and how to organize things, and the amplitudes are the same. At loops, they differ, and this one is, of course, simpler than QCD. But that's what we would call toy model. Yeah, in some respects, it's similar. In some respects, it's different. And there, as in the Kepler problem and the hydrogen atom problem, there is a hidden symmetry here, which is called Yangian. And for those who know, there is some connection to the 2D integrable models, because these typically have Yangian symmetry. But it's a great theory to test new ideas in QFT because of this high degree of symmetry and of the special properties. But from the other point of view, it's still fully interacting 4-dimensional quantum field theory. OK, so this is just to motivate why this is a good toy model to look at. And as I said, it's a very useful playground for many theoretical ideas in amplitudes, but not only amplitudes, in integrability. ADS-CFT correspondence was formulated for this theory. So it's a great it's a great platform to test new ideas. Okay, so let me just say a little bit about the n equals 4. So here, because it's a supersymmetric field theories, we work with the superfield. The superfield contains gluons and fermions and hermions. Oh. I guess I forgot one fermion and scalars here. Yeah, this is fermion and also the conjugate one. It has, in the expansion of the superfield, it has these fermionic variables eta tilde, which have index A, that runs from 1 to 4. And if we calculate superamplitudes now of these superfields, they can be organized using, they depend on n, number of external fields, and also on this k index, which is this number of negative helicity gluons. So if you look at the component amplitude, it means the number of the negative helicity gluons. But it's also, if you just take the amplitude, you can expand it in the powers of this eta tilde, and this k just picks the component eta tilde to the 4k. So that you can easily see that it picks k of these gluons and the rest of these gluons because they don't have any eta tilde, but of course it contains all the other amplitudes as well. And the planarity is, or why I call it planar, is that in this SUN gauge group, I set n to infinity, and already taught us that this is a very interesting limit from many point of views, the planar limit of SUN gauge theories. Now, there are many nice things about it, so let me just mention some of them. Of this planar limit. So generally, if we calculate loop level amplitudes, we have problems with variables. So we can do it using Feynman diagrams or using these unitarity methods. In these unitarity methods, we wouldn't have Feynman diagrams, but we would have integrals like that. Right? For example, at 2-loop 4-point, we would draw two different integrals. And there are also other integrals which contain triangles and bubble subintegrals. As I mentioned already last time, if we add this maximal supersymmetry, the only integrals that contribute are the ones which have box subdiagrams. So in this case, only these two diagrams contribute. But the problem is if we want to, the whole point of this research is to talk about the amplitude as one object. The problem is, what does it mean one object if I have two different diagrams where the loop momenta don't have really any meaning, because I can label loop momentum L1 here and L2 here, and there is, I cannot line up the labeling in one diagram and the other diagram, because I can also say that L1 is this one, or L2 is this one. There is no unique labeling of these diagrams, so there is no way how to sum them together. However, if we go to the planar limit, only planar diagrams contribute, and there is a way how to do it. There are global variables on the diagrams. And the main idea that the variables are associated with faces of the diagram rather than the edges. In that case, we can choose global variables, we can label all the diagrams in a unique way, and we can sum them together and get a one object, which will be the amplitude. So these are called dual variables. Now, that we can do in any planar theory, even planar QCD. Yeah, that just depends on planarity. And using these variables, we get, at loop level, we get a single function. Single, unique, well-defined function. So at tree level, it's directly the tree level amplitude. There is no integration done. But at loop level, there is this problem that we normally only talk about the amplitude because that there is no well-defined integrand. Each Feynman diagram has a different integrand, and we cannot really reasonably sum them. But in the planar limit, we can. Yeah, as I said, using these variables, we can factor all the integrations out, and we can be left only with a single rational function, which is called integrand, and that's the object to study. It's a rational function. There are no divergences. They only appear, the IR or possibly UV, if once we integrate. And in this theory, there is a hidden symmetry which exactly acts on these dual variables. In particular, these variables, these x variables that are associated with faces of the diagram, We can think that, about them as coordinates. They are related to momenta. Yeah, there is always the momentum flowing in an edge is a difference of these two coordinates which are adjacent to a given edge, yeah, to these faces that are adjacent to a given edge. And now this hidden symmetry, which is the analog of the hidden symmetry in the Kepler problem and hydrogen atom problem, there is actually a more precise meaning why it's related also. It's acts as a conformal symmetry on these variables. So this theory is conformal invariant, which means there is a conformal symmetry in usual position space, but then there is a second conformal symmetry acting on these variables. Okay, anyway, so there is some hidden symmetry called dual conformal symmetry, which exactly makes the theory special. By the way, because amplitudes in this theory are the same at tree level as in massless QCD, there is actually even a hidden symmetry in massless QCD at tree level, which nobody observed. It could be observed, well, it's in even in Young-Mills theory, or massless QCD only with quarks. So Young and Mills could observe it in 60s or 50s, but for actually see some implications of the symmetry, you have to calculate at least 6 gluonic amplitudes. And as I said, they were not calculated until late 80s. So people didn't notice that symmetry. It's there, but you can only see it once you go to very high multiplicities of amplitudes, which was not accessible that time. Okay, so I have to introduce one more thing. Well, the precise definition is not so important, but there are some variables which will eventually play a crucial role in the end of that talk, which are called momentum twisters. So I'm going to change variables again. So sorry for multiple variables for the same thing. And this is the definition. So I have n particles, I have n momenta, or n pairs of lambda, lambda tilde, or now n of these dual variables x. So by the way, if I want to think about these dual variables, they only make sense if the particles are ordered, just by definition. I have to order particles. Therefore, the planarity makes sense. The planarity is important, because in the planar case, I have the ordering of particles. Everything is on a plane, so I can just look at the particles that I can draw everything on a disk, and I just look at the ordering of particles at the boundary of the disk. So therefore, the particles are ordered, so the momenta are ordered. The momentum conservation means that if I just draw the momenta in a polygon, the polygon closes. And these variables are actually vectors associated with the vertices of that polygon, of this momentum polygon. And the edges are the regular momenta. And I can go from this picture to so-called momentum twister picture, when I just take the same kinematical information and package it in a different way. So this is the precise definition. I take a 4-component vector when 2 first components is the lambda spinor and the second 2 components is lambda tilde, multiplied with x a dot, which is just this matrix representation we already had before of this vector x. So there is some definition for that. But the important thing is that once you give me n momenta, I can take the same information and give you n vectors, 4 vectors. And in fact, these twisters are projective vectors, so I can always rescale it and don't lose any information. So these twisters are points in projective space P3. But there are 4-component vectors for us, which have which are rescaling invariant. Okay, so then using these new variables, so I can change the variables, but using these variables, the point of introducing them is that this hidden symmetry of n equals 4 planar n equals 4 super Young-Mills acts trivially on these twisters, just as SL4. They transform as vectors in this symmetry. I can use these twisters in any planar theory. Just the planarity is important, the ordering of external particles. But in this theory, it makes a special sense. And then I can build the invariance. If you later see some brackets like that, it means an epsilon contraction to 4 of these twisters. And if I can rewrite it in terms of original spin or helicity variables like that, yeah. Again, it's just change of variables. And if I take this box integral, I can then rewrite it using these twisters like that, because for the off-shell loop momentum, I cannot have a single twister that has only 3 degrees of freedom. I need a pair of them. I need a line in twister space. Okay, so this will play a role later, not now, but because it will be used later, I just introduced it. But it's a change of variables from momenta or spinor helicity variables to some to twister variables, which are vectors in projective space. Okay, now back to the on-shell diagrams. So that was just about the theory. So we picked this theory, which has some special properties. Now back to on-shell diagrams. And there is some interesting historic coincidence which happened with these diagrams. Because same diagrams appeared in mathematics around 2005, so roughly 5-7 years before we studied them, in a very different setup. Yeah, it had nothing to do with physics at all. And the motivation was following. Suppose I want to construct a k by n matrix of real numbers, where all k by k minors are positive. Yeah? So that was the mathematical setup. That was the question which was posed. This k by n matrix is modulo GLK. So it describes a k-plane in n dimensions. It's called Grassmannian. And there was something special about having the all k by k minors positive. So that's what mathematicians wanted to do. And the space of these matrices with these properties is called positive Grassmannian. OK, that doesn't seem interesting. Well, doesn't seem relevant to anything what I said. It's interesting in mathematics. And now there was an algorithm how to find such a matrix. It's very difficult if you just play with that. Even if you draw like 3 by 6 matrix, it's very hard to put numbers there such that all 3 by 3 minors are positive. If you do first 1,000 tries, you will definitely fail. So mathematicians wanted an algorithm to how to build such a matrix. And it's connected to many other things, which I don't mention, or mostly I don't even know. And they used diagrams which looked exactly like the diagrams I introduced before to generate that matrix. And let me just tell you what is the procedure, just for illustration, not that it will play a particular role in the talk. But the procedure is to draw a graph with 2 types of 3-point vertices, black and white. So that's kind of familiar, like this graph. And now label all the faces of the graph. So this graph has 5 faces. We use variables f0, f1, f2, f3, f4. And there is a property that if you take the product of all these variables, it's equal to -1. So there is always one redundant variable. OK. Now take the same graph and choose something called perfect orientation. So everything is graph theory at the moment. And the perfect orientation is that I put arrows on edges. And I put any arrows I want, but such that on white vertex there is 1 arrow in and 2 arrows out. And on black vertex it's opposite, 2 arrows in and 1 arrow out. So this is one way how to label this diagram. There are other ways. It's not unique, but there always exists at least one. So that's what was proven. Now, in this diagram, we have 2 incoming arrows and 2 outgoing. In general diagram, which would correspond to k by n matrix, we would have k incoming arrows and n minus k outgoing arrows. If we have a diagram like that, it would correspond to k by n matrix. This is 2 by 4. This is now 2 in and 2 out. Now, how do I construct a matrix? There will be an algorithm to take the element of the matrix, CAB. So it's a 2 by 4 matrix in this case. So A runs from 1 to 2, and B runs from 1 to 4. I'm looking at the paths. So for example, the entry of the matrix 1, 3 is related to a path from point 1 to point 3. So there is only one path if I follow the arrows here. And there are these phase variables. I will show it on next slide. And I take the product of all these variables to the right of the path. Yeah? So that's the rule. And if there are more paths, I have to sum over them. So This is the product of variables along one path, and if there are more of them, I sum over them. There is some normalization, so for example, going from 1 to 1 is equal to 1, or going from 1 to 2, where you see that 2 is incoming, I cannot really go there, that's 0. Yeah. That corresponds to some fixing of this GL2 symmetry in that case. Okay, so here is how I would construct the entries. So entry C1 free of the matrix, there is this path, these are these blue arrows. So I take the product of variables to the right of the path, F0, F3, F4. There are some signs here also I'm not mentioning. If I go from 1 to 4, that's an entry 1, 4. There are two paths, this one and this one. So I have to sum over both of them. The one is F0 times F4, and the other one is just F4. Yeah? So I just do it for all possible paths. And I construct the matrix. So this is the matrix that the mathematicians would construct based on that. And the statement for them is that there always exists choice of signs for f these variables f. In this case, these are these signs, such that all minors are positive. So this is an algorithm how to do it. If you choose these signs, all the 2 by 2 minors here are positive, which can be easily checked. Now, and this works for general, so if you take any graph, it's associated with a matrix using the same rules, which has positive minors. Okay, so what? So it's very interesting that the same objects appear in physics and mathematics in completely different setup. But maybe it's just that these are nice objects and they have many different interpretations. That sometimes happens, yeah, with many other mathematical objects. But is this mathematical construction, which looks, it's not complicated, but you have to follow some procedure. It doesn't seem to have any motivation for us to do at the moment, but is it useful for physics or not? So just the fact that the same diagrams appear wouldn't be so surprising, but the surprising thing is that it's actually connected to the physics picture. And okay, so on one side, we think about the diagram as a product of three-point amplitudes. Here, this is our point of view. And the mathematician's point of view is to look at the diagrams and write the metrics. Okay, now here is the connection. So the same formula that we can obtain as the product of 3-point amplitudes can be actually obtained from the C matrix. Now, the formula looks like that. I will explain what this delta function means on the next slide. But you just take all the variables that are in the diagram. So I said there are 5 variables here. I eliminate one of them using these overall conditions. So I decided to eliminate F2. I can eliminate, here eliminate F2. I can eliminate anyone you want. Okay, so here should be dF4 over F4, I'm sorry. So, and then I take the form dx over x for all variables of the matrix that parameterize the matrix, dx over x for all of them. And then there is some delta function. So now what it means, so in which sense this is equal to that. The delta function has a very, so I kind of globally denote it like that, but it has a very physics interpretation. As I said in the beginning of the lectures, there is something with the spinor helicity variables, which is a little bit odd, is that the momentum conservation is a quadratic condition. And I can try to rewrite, instead of this quadratic condition, it as a set of 2 linear conditions. So I put delta functions. Delta functions for me just means that this is a condition that I am imposing. So these conditions mean some linear relations between lambda and linear relations between lambda tilde. So they should reproduce the quadratic conditions between lambda and lambda tilde together. And in order to reproduce that condition, I get even a constraint that this matrix D of coefficients should be C perp, where C is the matrix of coefficients here. Okay, so going back here, so this is just momentum conservation. It's a relation, it's a constraint it's a reproducing momentum conservation as linear conditions on lambda lambda tilde, where C is the matrix of the coefficients. Okay, so from the practical point of view, I take this thing, which only depends on C and lambda lambda tilde in some very trivial way. It's just momentum conservation here. The C matrix is the non-trivial part, and I just use these delta functions to calculate for the parameters of the C matrix in terms of lambda lambda tilde. And in the end, I get some function of lambda lambda tilde, and that would be the same thing as this. So that's the connection, and that's the procedure. And now for arbitrary on-shell diagram, I can do exactly the same. I follow the mathematical procedure. I construct the matrix. And once I have the matrix, I have everything. I can calculate the diagram using the same logarithmic form. So this is dx over x, which is also equal to d log x. So I call it logarithmic form. And these two things are the same. So once I have the output of the mathematical calculation, I can trivially turn it into a physics answer, which calculates the same diagram as a product of 3-point amplitudes. Now, why is this true, and why is it for n equals 4, and why is it not for other theories, or how is it related? It seems completely ad hoc. Now, the connection of these diagrams and the Grassmannian is very general, because before I specify that this is the formula, the Grassmannian matrix is associated with the diagram. So if I give a different interpretation of the diagram in different theory, I don't use this theory, but some other theory, which also has 3-point amplitudes. These things are connected. Of course, I have to write this form in order to say how to calculate the diagram using this mathematical information. Now, what is specific for theory is exactly that formula. It's this form. So I used f variables there. Now I use alpha here. But it's saying how to calculate the diagram using the information about the C matrix. And again, as I said, this is a trivial delta function, and the purpose of the delta function is to reproduce momentum conservation in terms of lambda lambda tilde. In addition, it solves for these variables alpha in terms of lambda lambda tilde. So there is no form in the end. Yeah, we are solving for these variables in terms of lambda lambda tilde. There might be some variables left if they are in on-shell diagrams, but let's not discuss it here. Okay, so in planar n equals 4 super Young-Mills, this is the connection. Now, in general quantum field theory, there is some form, it doesn't look like that, it's probably not as simple like that, which calculates the same diagram, again, using this information from the matrix. So in a sense, this form F alpha is a definition of the theory, as Lagrangian does. So instead of Lagrangian of n equals 4 super Young-Mills, I have to give you this form. In other theories, I don't know, QCD, where actually from massless QCD we know what the form is. But in any quantum field theory, there exists some form which calculates that diagram using this mathematical information. So in a sense, it's a definition of the theory like the Lagrangian is, but in a very different setup, in a setup of these on-shell diagrams and the differential forms.
Sorry.
Yeah?
Still always for the planar limit?
Not necessarily. Yeah, okay. Well, that's a good question. It's not for the, there is something special about the diagrams in the planar limit, but they have some, there are some nice mathematical properties, but not necessarily in planar limit. We can draw non-planar diagrams as well. And that's right. So then then it's not ordered. So there is not dispositivity condition. Yeah. So that's a very good point. So if the diagram is planar, they are ordered. I write a k by n matrix, and then these k by k minors are positive. The positivity depends on ordering, because if I flip two columns, I change it to negativity. Now, if the diagram is not planar, I can still write a k by n matrix, but there is no sense of positivity, because that is associated with ordering. Yeah, if there is no ordering, there is no positivity. but I can do it also non-planar. OK, so that's the relation between the diagrams and the theory. So, and this form. So there are kind of two steps, because I said that these diagrams we can calculate from physics in any theory. We don't know how to get amplitudes from them yet in any theory. Now, if we go farther to this mathematical formulation, there exists some form in any theory, but we don't know it in all theories. We actually know it beyond this special case, but we know it in supergravity, we know it in planar QCD, but not in general. There is no general, there is no way how to say for all theories what this form is, but it's an open question. It should exist, so somebody should find it. OK. So now let me wrap up that part. So at least for planar n equals 4 super Yang-Mills, we established that this thing in the blob is a sum of on-shell diagrams. So this is, for tree level, it's for more theories. But for full generality to all loops, this is what it is in this blob. It's not just Feynman diagrams, but it's also pictures like that. And hopefully, in following years, this will be done for other theories. And there will be some more uniform picture how these diagrams play a role in physics in general. Now, but even for planar n equals 4, this is not completely satisfactory picture. Because I was saying that I was looking for a single object, that the amplitude is a single object fixed by constraints. And then you can rewrite it using in some expansion, like Feynman diagrams or on-shell diagrams. But it's still a sum of objects. And furthermore, this sum is given by unitarity. How do I know that it's these 3 diagrams and not some other 3 diagrams or 5 diagrams and so on? This was the thing that told me that was these recursion relations. And recursion relations is just unitarity. Just saying that the amplitude factorizes on these poles, and I have to sum over all these factorizations. OK, so despite these individual diagrams have very nice, have completely different way how to talk about it in terms of these Grassmannian matrices and these differential forms, which is completely alien from the point of view of amplitudes. Still, the fact that I have to take these 3, the sum is given by physics, not by mathematics or anything else I would like to land on in the end. OK. So I'm still searching for a single object for the amplitude, for some completely new definition of the whole amplitude, not just pieces in the amplitude. OK, and what it can possibly be. So even before, actually, these on-shell diagrams were found, there was a very interesting observation back in 2009, which pointed in certain direction. And Andrew Hodges studied the 3-level scattering amplitudes for a particular gluonic gluonic amplitudes for particular helicity. So this was amplitude 1 minus 2 minus 3 minus 4 plus 5 plus 6 plus. We already discussed that amplitude before. So he used BCFW recursion relations. There are 3 diagrams that contribute. The middle one is actually 0 for that particular helicity configuration, because here we have 3 minuses, and even if we put plus on the internal leg, it's still a vanishing 4-point amplitude, so there are only 2 contributing. But he studied that in this momentum twister space, so therefore I introduced these variables before. And, well, let me not talk more about the calculation, but the point is that if you take this diagram, take this 5-point amplitude here, 3-point here, evaluate it, everything in terms of lambda, lambda tilde, and now you change the variables to these z's, to these 4-component vectors, which are projective, so they have only 3 degrees of freedom. Then if you do it, for this diagram, you get this relatively simple-looking expression, and for that diagram, you get this relatively simple-looking expression. So it's a cute way how to write it. Now, I just remind you these brackets, 1, 3, 4, 5, it's just a 4x4 determinant of z's, z1, z3, z4, z5, or in other words, it's an epsilon contraction of these 4 vectors. Anyway, you can just look at it as some labels, 1, 2, 3, 4, 5, 6. corresponding to 6 particles. Okay, so what is interesting about it is that he found that well, this would be just rewriting things in terms of new variables, but in these new variables, this expression actually has an interpretation of a volume of tetrahedron where the vertices of this tetrahedron are given by these brackets in the denominator, so there is some map between it, in this twistor space. Yeah, so this expression is equal to the volume of this object in the twistor space. So this was his discovery. It was a very surprising connection. And you have this tetrahedron for this expression, this tetrahedron for that expression. Now, this thing, 1, 2, 3, 5, is related to a spurious pole that I mentioned already earlier in these recursion relations. Now we just rewrite it in this momentum twistor variables. And this spurious pole is related to this spurious phase between these two tetrahedra. And if you glue it together, the volume of this picture is the 6-point amplitude. Yeah? So amplitude is a volume of polyhedron in this space, this particular amplitude. Yeah? So that was his discovery. So here, not only that the amplitude is a single object, of course, we can cut it into half and get these two pieces if we want. But furthermore, there is a connection to geometry. It's a volume of something. Yeah? There are no particles, no interactions, there are no diagrams, nothing like that. It's a geometry, it's a volume of it. And of course, the way how the momenta enter the game is through the vertices of this, because the vertices, it's in the projective space P3, the vertices are these momentum twistors, and the momentum twistors are related to momenta, but here they just play purely geometrical role as vertices of some geometrical object. Okay, so unfortunately for that case, this was true only for this special case, and extended a little bit farther to some tree-level amplitude with some special helicidae, but it seemed like a just curious observation which doesn't generalize. Yeah? Because this wasn't true. People were searching, you were searching for that for a number of years, but it just wasn't true that the other amplitudes were volumes of some polyhedra in this momentum twistor space. It was just not true. Okay, but still this idea that amplitudes are volumes of some region in some space, so this wake conjecture, was still around. But then learning the lesson from these on-shell diagrams told us that it's not this momentum twistor space, which is the right space. It's not the projective space, but it's this Grassmannian space where we should generalize it. But of course, as a physicist, you would have no idea what this thing is. So unless you hit it, or you hit mathematicians that know about it, you would never think that something like that might be relevant. Okay, and now, well, there is a long story, and I don't have much time. So let me take one particular path into the story and just say a little bit about it. But the strategy how to generalize this Hodges picture to all amplitudes in this theory is to use some simple intuitive ideas, so thinking about these tetrahedra, and actually we will even go back and not think about tetrahedra, but just on a plane about triangles and polygons. This is the simplest case that we can have. There is actually no physical amplitude that is associated with it, but it's kind of a some toy model for the amplitude, and that actually generalizes. The polyhedra is actually the first advanced case. Now, we use suitable mathematical language to describe these simple geometric ideas, and that generalizes. Yeah, it will be the algebra that generalizes, not directly the intuition. Okay, so let's talk about triangle and polygon, because that's where everything started and where we can understand most of the story. Okay, so let's think about the inside of the triangle. So we have 3 points on a plane, and now it's a projective plane. So I'm aware that projective geometry is not extremely common subject, but the points here, the projectiveness here says that, well, the z's, these points are 3-dimensional vectors, but there is this rescaling, so Z and TZ are identified, which means that I can, for example, fix the first component to be 1, and it's only these two components which are independent. Then I can talk about the interior of that triangle, so I can just connect it with lines, and I want to describe a point which is inside that triangle. So how do I describe such a point? So I write Y as a linear combination of the vertices. And now the constraint that this point Y is inside the triangle is that all these coefficients are positive. Yeah? If the coefficients are positive, I'm inside the triangle. If one of them is negative, I go outside with Y. Now, because it's projective, so there is this relation, I can always fix one of the C's to 1. Yeah? So there is always the overall, I can rescale both sides of the equation by some number and nothing changes. The geometry is the same. So that's the nature of projectiveness. So I can, for example, divide both sides by C1. So this fixes C1 to 1, and it's the same geometry. So that's the only way how the projectiveness enters the game. OK, now suppose I want to take Y and go on a boundary. So I want to go on a boundary on this line 1, 2. So that means that Y is now linear combination of Z1 and Z2. That means that I have to set C3 to 0. So if I set C3 to 0 in this expansion, I am going with Y on that boundary. If I set C1 to 0, I'm going on that boundary. If I set C2 to 0, I'm going on that boundary. Yeah, I hope it's clear. OK, if I set C2 and C3 to 0, I kill these two terms, and I'm saying that Y is C1, Z1. But because everything is projective, C1, Z1 is the same as Z1, then I'm just going to this point. Yeah, I'm moving Y to the vertex. So that's going to the second boundary, if you want. OK, and now I want to associate a logarithmic form with that picture. So it's a form with logarithmic singularities on boundaries. So whenever I go on the boundary, it blows up like dx over x. And the form here is just this form. So now I really fix C1 to 1. I get this expansion. And the form is just that. And you can see that if I go to the boundary C3 is 0 to line 1, 2, there is dC3 over C3. So I just erase it. I take the residue on C3 is 0. I get dC2 over 2. And if I go another boundary, I set C2 to 0. If I go on the C2 0 boundary on a line 1, 3, it just reproduces this form. Then I can go to the second boundary, it just gives 1. And all the other boundaries are accessible when I also set C2 and C3 to infinity in some different combinations. OK, good. So I have a triangle. I have a point inside the triangle. And I wrote some form which blows up on the boundary like dx over x. OK, now, for some reason, I would like not to write the form using these C variables, which are expansions of Y in terms of Z1, Z2, and Z3. But I would like to write it directly in terms of Y, Z1, Z2, and Z3. Yeah. There, in a minute, you will see there is a very good reason why I want to do it. And for that, I have to take this equation and dot it with, for example, Z1, Z3. That gives me the C2 coefficient and so on. So, well, I will not go through that in details, but this form is actually equal to that form when these three brackets are just epsilon contractions of 3 of the vectors, or it's a 3 by 3 determinant. You can see that whenever Y is a linear combination of 1, 2, this blows up. When Y is a linear combination of 2, 3, this blows up, or 3, 1, it blows up. So these are the poles of that form. It blows up on the boundaries, and this is just the measure. OK, so that was triangle. And now I will do it also for polygon. The polygon has similar definition. So I have a convex polygon on a plane with ordering 1, 2, 3, 4, 5, 6, or up to n in general. There is some constraints on the z's I have to impose in order to be convex. It's some positivity constraints, which is some reminiscence of this positivity story. But now Y is a linear combination of all the Z's with positive coefficients, not only 3, but all of them. And if you do that, you span the interior of the polygon. OK, now I can triangulate the polygon in terms of triangles. So I can divide it in terms of triangles. And then in each triangle, I write Y as a linear combination only of the 3 Z's. And there is this natural form that I write in terms of inside each of the triangle. Yeah? So this is the first triangle we had before. Then there is a second triangle. Now the variables are C3, C4, and so on. Now the thing is that there are now too many variables here, C2, C3, C4, C5, C6. I would like to sum the forms together. I would like the form on a polygon, but that's not possible to do in terms of these variables. It should be still 2 form, because it's a 2-dimensional space in the end. So I have to first rewrite it in terms of the Y's and the Z's, in terms of these forms, and now I can sum them because they have the same measure. It's a form on Y. So I can sum them, and then these poles, Y31, Y41, and Y13, these are the same up to just flips. This is the line 1,3, corresponds to these spurious boundaries that they cancel. So if you sum everything, these lines, the dependence on these lines cancel. So these are spurious poles. This is kind of similar to the spurious poles in the amplitudes, or in the Hodge's calculation. There was this spurious phase. Now we have only spurious lines. So in the end, the form that we get is something like that. It has only 6 poles corresponding to 6 boundaries, and then there is some non-trivial numerator here. OK, so yeah, I'm near the end of any technical part. I just want to show what is the type of calculation we are doing. So now this is a form on some Y space. Yeah, so it's some Y, which is a point inside a polygon. How do we can possibly get an amplitude from that? We would like some amplitude, which is a supersymmetric function. And the Y actually hides supersymmetry in certain sense, because we can rewrite the Z's as 2 bosonic components and 1 more component, which is a dot product of 2 fermions. One of them is the fermionic component in the expansion of the superfield. It's the fermionic variable. And the other one is some auxiliary variable. Anyway, then I define Y0 to have 0, 0, 1 only in this third fermionic component, or there are products of 2 fermions. And if I do some integration over this auxiliary variable, I localize Y to Y0, I get a function which now doesn't depend on Y, but is supersymmetric. So this is just a baby version, how we would do it in the actual case when it corresponds to the amplitude. But this is, I just want to show that there is a way how to embed the supersymmetric function as a bosonic form on geometry. And this is the connection between 2 of them in this very particular case of triangle and some simple setup. Because this already looks a little bit like some amplitude. It's not directly an amplitude. It's some very simple toy version of the amplitude, but generalizations of that would be amplitudes. And that leads to the amplituhedron. OK, so now let me say it just in words. So the amplituhedron, it's some geometric object. It's a space specified by some set of inequalities. And it's a generalization of the polygon. So in the polygon, we had this inequality that Y was linear combination of external edges with positive coefficients. So that generalizes. And the full definition actually fits on one slide. And the polygon is the first example of the positive Grassmannian. Some very simple example. The generalization go to the Grassmannian space more deeply and even generalize it. Then we have some logarithmic form on the boundaries of this space, as we had the logarithmic form on the boundaries of triangle and then polygon. And L-loop amplitude in planar n equals 4 super Young-Mills, the integrand of the amplitude, can be extracted from this logarithmic form, similar to the games I played before, extracting a supersymmetric function from the form on previous slides. Yeah? It's a complete analog of that. So this is that's the statement. Now, one way what I can do is first triangulate that space in terms of some simplices. It's like triangulating the polygon in terms of triangles. Then the form is trivial. It's just the form dx over x for all variables. Like in case of the triangle, it was just dc2 over c2, dc3 over c3. Now, the triangulation is the complicated part. The form is trivial for each piece. It's a set of regions which cover the whole space. And each region is specified by some variables which goes from 0 to infinity. Now, this is exactly what the on-shell diagram gives us in one particular triangulation. So this BCFW recursion relations provides us a triangulation where these pieces are on-shell diagrams. I said there is this connection to the Grassmannian between the diagram. This Grassmannian matrix is exactly the analog of a triangle that I showed before, generalized to this Grassmannian space. And then we have to sum them. So this is another road how to extract the result from the geometry. Okay, so instead of, so that's the story. We have this geometric space. We know the definition to all loop orders in all amplitudes in the theory. There is some form which is defined on the geometry, and from that form we can extract the amplitude using some simple algebraic procedure. So the physics doesn't enter the story in any way. The only way how the momenta, the kinematics enter the story are in the positions of vertices of this geometry. Now so that's the definition. Of course, there are many challenges, especially how to triangulate that object and calculate the form. So instead of saying something more general, let me give you one particular problem to show how the geometry gives us some set of inequalities. We can interpret them in some way. And there is an infinite class of problems which can be interpreted in a very nice way. So let me just present it. If I get two gluons to two gluons in this theory to any loop orders, it can be formulated as a simple looking problem on positions of vectors in positive quadrant. So I have a positive quadrant, and I put some blue and red vectors there. And it's positive quadrant because if I write these vectors as, well, these are two component vectors, they have positive, the entries are positive variables. So x1, y1, z1, w1 are positive. And now I want to write a form on the space of all these configurations. So in this case, it's just this simple logarithmic form. Now, if I change the variables, this gives me a one-loop amplitude for 4 gluons in this theory. Because these x, y, z, and w directly corresponds to loop variables in a very simple way. Now, I add another pair. If I do it, I just double everything. That would be simple. But now I impose a constraint that if I have 2 blue vectors, and I take the vector of differences, and 2 red vectors, and I take the vector of differences, I don't want on configurations of these vectors. I just want the ones where this angle is bigger than 90 degrees. So I want to choose a subset of these vectors. This kind of triangulates the plane of all these vectors, only keeps the ones that I want. There will be 8 different sectors, actually. And the mathematical question is find all such vectors, all ranges for these x, y, z, w variables, such that this condition is satisfied. Once you do it, I can easily turn it into a 2-loop 4-point amplitude in this theory. And actually, in terms of that, it looks like that. So it has some little bit slightly non-trivial part. And now the general problem to any loop order is that I have L red vectors, L blue vectors, and they pairwise satisfy this inequality. So any differences of reds and the differences of blue, they need an angle bigger than 90 degrees. And you have to find all configurations of these blue and red vectors. This effectively triangulates this amplituhedron for this case. And once once you are able to solve this geometry problem, then you can easily turn it to the L-loop amplitude. So this can solve, actually, this problem of 4-point scattering in this theory to any loop order. And because this theory is very nice, doesn't have any non-perturbative effects, this would be actually an exact formula for 4-point scattering in that theory. Okay, so why all this is true? Of course, there is no quantum field theory proof, because we didn't start with anything which looks like physics, so there is no derivation, there are no recursion relations, there is no Lagrangian-based derivation, nothing, because we just say that there is this geometry and there is this volume of this geometry or logarithmic form. So why is it correct? Well, it's correct because despite we cannot start with n equals 4 Lagrangian and show that it gives the same amplitude. That's absolutely impossible. But we can show that whatever we get as a result for this differential form, it satisfies the properties of locality and unitarity. So that form factorizes. The only poles are local poles, and it factorizes using these two pictures. And that's enough, because these two things, locality and unitarity, in this form completely fix the answer. So if we get something which satisfies these properties, it's the right amplitude. So it's a very indirect connection between physics and this mathematics, but that's why it's true. So it's totally different approach, but it's the same answer. We are calculating the same function. Yeah, we are not calculating anything new, so once it satisfies these constraints, it must be correct. Well, now there are many open questions. Of course, there is question about this triangulation. There are also many questions about mathematical structure, especially, well, this is for this special theory. There is question how it generalizes to other theories. We know that on-shell diagrams generalize to other theories. We don't know about the recursion relations there and so on. This is even going much farther. We have no idea how this would generalize to other theories, but it's kind of a tip of the iceberg where we can go in this direction of reformulating the question of scattering amplitudes. And note that it's also a very different picture, because the picture of dynamics of particle interactions in 4 dimensions, where the Feynman diagrams directly gives us this picture of dynamical processes, is now replaced by some static geometry in higher dimensional space. Yeah, there are no particles here, no fields or no exchanges or nothing like that. It's just some geometry which lives in high dimension, and it gives us the same answer. So back to the question, what is the scattering amplitude? So in this special case, we can also give an alternative answer, and it's some geometric object. Now, of course, this is step 1.1.1 in some long process of trying to reformulate the scattering amplitudes and maybe quantum field theory in more general. One has to do other theories and also at masses understand RG flow correlation functions. Amplitudes are not the only objects in QFT. Of course, in other theories, one has to go beyond perturbation theory. And the other question is to establish it as an efficient computational tool and eventually to be able to produce the results using that as well. Now, let me end with some fantasy, which might be completely false, that maybe it can help us even with some deeper questions beyond quantum field theory. And the motivation comes from even classical mechanics, when we know that we have 2 different formulations of classical mechanics, which is Newton's equations and action principle. They are completely equivalent. Now, if we start with quantum field theory and we go to the classical limit, we end up with this formulation, not this one. Yeah, despite they are completely equivalent. Now, there is a long search for quantum gravity. This is not about gravity. There was no gravity in this amplituhedral picture. But maybe if if we have a theory of quantum gravity and we go to the weak gravity limit, maybe, and there are many reasons why we shouldn't land on the standard formulation of quantum field theory as we know it. There are many problems with that, incorporating gravity. If there is some different formulation, it's possible that the weak gravity limit of our ultimate theory would actually end up here. And maybe this geometric formulation is exactly going along these lines. But future will say. Of course, we have a theory of quantum gravity, and that's a string theory. And we have string interactions which look very much like Feynman diagrams, but it's interactions of strings, not point-like particles. So in this fantasy world, maybe the right question is, what is the new geometric picture for string theory that would eventually might lead us to the theory of quantum gravity? But now back to the amplitudes. So what I showed in this last presentation is just one of the direction in very fast developing fields. People are doing many different things. Yeah, amplitudes is not just a single thing, calculating amplitudes. There are many different approaches. And it actually spans many of the activities in the QFT community. There are many zeroth order problems which are open, including the ones I showed, and there are many chances for young people to make big discoveries in the next few years and make big impact. For those who are interested, there are already some books on scattering amplitude, some very nice reviews, and we have many conferences, and there are also summer schools. So for the ones that are interested, there is actually a summer school in July in Edinburgh where you can still apply and learn more. Thank you.
Thank you.